Rahim. The topic I'm presenting today is one compartment IV bolus models. So before really diving into my topic, I will just go through pharmacokinetics and models in pharmacokinetics in a nutshell. So pharmacokinetics is the mathematics of how the body absorbs, distributes, and eliminates drugs. So all of the pharmacokinetics is based on models. So here is a very simple kind of model. We have a vessel A from which the liquid is flowing at a rate into vessel B. So suppose that we know that the flow rate Q is equal to 10 milliliters per minute, and we also know that the time it takes to fill vessel B is equal to 8 minutes. So from this data we can calculate the volume of vessel B, which will be Q into T. So it is going to give us 10 into 8, which will be equal to 80 milliliters. So by incorporating this data into this model, we got to know that the volume of vessel B will be equal to 80 milliliters. So this was a really simple kind of model. So what we do is that we can add further information into this model to build a more complex model, so that we can predict more accurate results. For example, if we add information like we know the evaporation rate of this liquid. For suppose we know the evaporation at any temperature, which might be anything like x. So from this, now our equation for volume of vessel B will not be Q into T, but as we have added much additional information to get more accurate results, so now our equation will shift to Q into T into E at any temperature, or you can also take that value x. Okay. So this was what I really want to tell about the models. So we build simple models and then we build over those models. So we build models to widen the scope of our experiment and provide much accurate results. So in a similar fashion, pharmacokinetic models are built, which tell us that how our body handles the drug. So there are simple models, then ranging on to much more complex models. But for my part of this presentation, I will be only discussing the IV bolus model, one compartment IV bolus model. So the next thing is that when we design a model, obviously we need some kind of data to incorporate into that model. Suppose what we did in the model we just discussed is we had the data of the flow rate and the time. Similarly, we need data for our pharmacokinetic models, which are obtained by doing various experiments onto human subjects. So what we do is that we administer our drug into various human subjects, and then we obtain various data from those subjects, and then we take an average of all the data so that we can obtain one single value on which we can perform our studies to calculate various pharmacokinetic parameters. How the data is acquired. So what we do is that we administer a known amount of the drug to our human subjects, and then we collect blood samples from those subjects at various time intervals. After collecting those blood samples, we centrifuge that blood, and by this way we get plasma to separate it, and then we use that plasma to analyze or determine the concentration of our drug. After getting the concentration of the drug, we get the data sets of drug concentration at various time intervals, from which we can plot, graph, and do further studies. So two things are to be kept in mind. Firstly, that the drug that we administer is metabolized in a body and is also present in a blood in a metabolized form. But what concentration we are looking for is not the metabolized one. We look for the unchanged concentration of drug, and as the time passes on, the unchanged concentration of that drug decreases. So evaluating that unchanged concentration of drug, we get our data and we build or plot graphs, and through which we can calculate various pharmacokinetic parameters. The second major thing is that from the blood samples, we don't use the blood as the blood for analyzing our drug concentration, but we use the plasma. So why is that we use plasma but not blood? Because blood contains various cells and clotting factors, which make it difficult to analyze our drug concentrations. So it is a very important aspect of pharmacokinetic studies that we use plasma as the medium for analyzing our drug concentrations. So the next thing is that after getting that data values, we put them into various pharmacokinetic equations. These are certain kind of mathematical equations built according to our model, based on our models. And after putting that data into our equations, we get certain mathematical descriptions of how body handles the drug, which are also known as pharmacokinetic parameters. So after putting the data into equations, we get parameters, and those parameters are also interlinked with one another. So I'm starting with one compartment IV bolus model, but I will not discuss all the pharmacokinetic parameters in this presentation. I will be just discussing some of the major ones. So one compartment IV bolus model. So what we do is that we administer our drug intravenously through an IV shot, and it distributes through in a body as a one compartment, and it is eliminated from the body via first order rate kinetics method. So the first parameter is the elimination rate constant of the drug. So it is the fraction of drug lost from the plasma per hour. With the increase in time, you can see that the drug is being lost as and the fraction at which every hour the amount of drug has been lost is known as the elimination rate constant. So elimination rate constant is also the slope. So as the drug is being lost through the first order kinetics method, and I'm not dealt with the first order kinetics video in this video. According to that equation, when we plot the graph for the first order rate kinetics, the slope we get is also equal to the elimination rate constant. So the formula for calculating an elimination rate constant from our data set or from the graph which we have plotted from the data is by calculating the slope of the line. So this is the formula of how we get our elimination rate constant. So what we will do is we will solve a question related to the elimination rate constant to get a better understanding of what we are doing.
Okay, so here we've got one question for an IV bolus question, and I'm going to calculate the elimination rate constant from this given data. So a 50 kg woman was given a single IV dose of an antibacterial drug at a dose level of 6 mg per kg. Blood samples were taken at various time intervals. The concentration of drug was determined in the plasma fraction of each blood sample, and the following data were obtained. So this is the data of the drug concentration with respect to various time intervals. So as you can see, the drug concentration is decreasing. So how we are going to find the elimination rate constant? So coming to the formula, we're going to take two values from this data set. I'm going to take the first two ones. So lnC2, which will be ln 7.87 minus lnC1, which is ln 8.21.
Yeah, so now we're going to divide this by we're going to divide this by 0.50 minus T2, which is T2 minus T1. So the answer we get after solving this equation is 0.17, and the units for elimination rate constants are per hour. So our answer is 0.17 per hour. So the next parameter is the half-life. So half-life is the amount of the time it takes for the plasma concentration of the drug to fall by half. So this is the equation of how we calculate the half-life for our given data set. So this equation is also derived from the first order rate equations. I have not made those equations in this presentation, so I will not be going into the derivation kind of stuff. But this is the main crux, which is for the half-life, and we are going to solve a question to make more sense out of it. So a sympathetic volunteer is given an intravenous dose of an antibiotic, and serum drug concentrations were determined at 2 hours and 5 hours after administration. The drug concentrations were 1.2 and 0.3 micrograms per milliliter respectively. What is the biological half-life for this drug using first order elimination kinetics? So as we know, we are asked to find the T half-life of this given data set, but what we require is the elimination rate constant to find the T half-life. So from this data set, we can find the elimination rate. So how we going to do is which is equal to ln C2, which is 0.3, minus ln C1, which is 1.2, and then we will be dividing it with the time frame, which is 5 minus 2, T2 minus T1. Yes, basically I'm not able to draw that line. So the answer for this is 0.46, and the units for the half-life. Just wait a second, I'm trying to open subscribe. Yes, okay, you can write like this. I'm not able to figure it out. So, okay, the next thing is we're going to find the T half-life, which will be T. It's very big. T half-life will be equal to 0.693, and it is divided by 0.46, which will be giving us the value of half-life. So the value for T half-life will be 1.5 hours. So the next parameter is the volume of distribution. So it is the volume of drug which distributes in the body. If the drug is distributed much more into the body, like in various tissues, compartments, so the volume of distribution will be more. But if more of the drug stays into the blood, then the volume of distribution is going to be less. So here it is. The formula for VD is dose divided by plasma concentration at any given time. So here we know the dose of the drug we are going to be injecting. There is another concept. If more of the drug is distributed into various body cells and compartments, so the volume of distribution will be more. But if it stays in the plasma and is not distributed elsewhere, then the VD will be less. So we're going to solve a question for VD as well, and we are going to use the same question we did before for elimination rate constant. So for this, we first need the dose of the drug. So the dose of the drug will be 6 into 50, as 6 mg of drug is given per kg of the weight. So the woman has the weight of 50 kg, so the dose will be equal to 6 into 50, which is going to give us 300 milligrams. Okay, so the next thing is VD, which will be the dose, which is 300, and we will divide the dose with the plasma concentration. So if we take this concentration, then we will know the volume of the drug distributed at this time. If we take this concentration, we will know the volume of distribution at 0.5 hours. So what we are going to do is we will take the concentration at time 0. So as we know, we don't have the concentration from time 0. So if we plot a graph and then we extrapolate that graph, we're going to get the value for time 0. So it might be somewhere around 8.4 to 8.45 as the graph suggests. The data suggests. As I'm not plotting the graph, so I won't be able to extrapolate those values for in this presentation. But we are just assuming that it might be 8.4 at time, which is 0. So if we divide by 8.4, we are going to get an answer which will be equal to, which is equal to 3.65 liters. So this is RVD 3.65 liters. So these were the three parameters which I discussed: the elimination rate constant, the half-life of the drug, and the volume of distribution. We can also calculate other parameters, and I'm not going to do them in this video, but I'm going to just show their equations of how you find it. So this is the half-life. So there are also as I told you before, that all these parameters are interlinked with one another. Okay, so we can find different equations to find one parameter, and all these equations are derived from the first order rate equation, which I already have told, I've not discussed in this video. So what I want to say is that it is important to, what I think is that you need to know, like you don't need to memorize, but you need to at least know that how these equations are derived from that rate equation, so that you might get a better understanding of how this whole system is working. So we will just look at some of this. The half-life, we have done this one, and we can also calculate half-life with these equations. If we know the concentration, we can plot graphs for any time interval, VD and half-life. Similarly, we have got equations for clearance, duration of action, how long our drug is going to work, the concentration of drug in the body, and this is the main equation for the dose. These are the equations for elimination rate constant. As you can see, we have 5 equations dealing with this. Similarly, the percent, if you want to know the percentage of drug remaining in the body, we can do with this equation, and then the fraction of dose remaining in the body and the fraction of drug dose eliminated. So this is what I have for this presentation. I hope you enjoyed it. Thank you.